So welcome to part 2 of this tutorial. Just to recap, what we've done so far is set up a very simple fluid simulation. We've then brought in the particles from that fluid simulation and used them to transfer an attribute to some points scattered on the surface which we will later want to shade as either wet or dry. And in fact we can visualize the group by having a look at the display. Make sure we're on the right node, and we will ghost other objects, hide other objects rather, and we can see that the yellow points here are the ones that are selected as part of this group. And as we run the simulation on, what's happening is that as the liquid moves, these points are coming in and out of this group. So it's only half of the solution. What this doesn't do is preserve wetness in areas where the liquid has flowed over but has now left. What this does is give us wetness only where the liquid actually is at this frame. And to speed up this a little bit more, I'm going to set the frame distance to 100, the frame range to 100. And let's run that again. And we can see that we're not getting the wetness preserved here. There are several methods to allow these points to remember, if you like, the wetness. The one we're going to use involves setting up a particle network. We need to do that because in a SOPS network, like the one we have here, everything is re-evaluated at each frame. It doesn't store information from the previous frame. You can't go back and ask whether or not a point was part of this group at a previous frame or not. Only looks at the present frame. A POP network, however, stores points from previous frames and thus can maintain information from frame to frame. Let's see what I mean. I'm going to rename this group wet points, and let's put $OS in here so that the group itself is called wet points. There we are. And I'm going to lay down a POP network. Dive into it, lay down a source, and we're going to use the first context geometry, and we're going to use a source group, which is wet points. So we're only going to create points for the points which are in this group, wet points. Points ordered is what I want to do, but I want to change some attributes on the birth tab. I don't want constant activation, I want activation at every frame, and the birth rate is going to be $ngroup. Now what $ngroup gives me is the number of points in this group here. So what's going to happen is that at each frame we're going to create $ngroup new points. Let's set an initial velocity so that it's 0, and those points are just going to stay exactly where they are. Let's go back up. Now if we have a look at this POP network and run the simulation, we can see that what we're getting are points that show where the liquid has flowed in previous frames, That's because the pop network is remembering the particles it created last frame and the frame before that, and they're all stationary, so they just stay where they are and map out where the liquid has flowed. So let's create an attribute. This time we'll call it pops wet, and again I'm going to give it a value of 1. And now I want an attribute transfer sop, and I'm going to be transferring it to this geometry here, and we're transferring point attribute, and the attribute we wanted to transfer is pops wet. Now if we group this according to the expression what we should find if we run the simulation, but let me just set the conditions here. I'm going to put this down to 0.1, and let's run the simulation again. And of course this is a point group rather than a primitive group, so let's run that through, and we can see we now have some points which are either liquid, near the liquid and thus wet, or not. And this essentially is what we're going to use to create our render. But there's one more step, which is to write out these points as a point cloud, which we will then use when we come to render.